I'm Lucas, or online I go by the tag Rukai. Today I'm going to talk about a hobby project I built in Rust. I'll go through a bit of backstory of why I wanted to build it, and I'll talk about the Rust technologies I used and why I chose them. It'll be a bit haphazard, but hopefully it'll give you some ideas for your own projects. If you've been coming to these Rust meetups for a while, you might remember a talk I gave about my Super Smash Bros.-like game I was developing in Rust. But since then, a problem I had was that I had a game engine, but no content for it. So an idea I had was to write an exporter that reads content from Super Smash Bros. Brawl's game files and exports them into a format understood by my game. The idea being I can distribute the exporter in-game, allowing users to run the exporter on their own copy of Brawl. Obviously, I can't redistribute Brawl. As you can see in this video, the idea worked really well, but at the end of the day, it was still just a poor imitation of an already existing game. So the rest of this talk isn't about the game, but something else that I spun out of it. Before I continue the rest of the talk, I'll have to quickly explain frame data. Typically, fighting games display 60 frames per second, and the game performs one tick of game logic for each of those frames. Frame data is analyzing what happens on every frame of a move their character performs. For example, here we have Ike's forward air. The yellow sections are the hurt boxes. They show where the character can be hit. The green, blue, purple, red, orange circles are hitboxes. They show where the move can hit other characters. Developers and players alike will compile and organize notes on frame data to better understand which moves are stronger than others and what circumstances different moves should be used in. If you are playing a character, these are the properties you want your moves to have. The first frame that hitboxes appear on should be as low as possible. The earlier the hitbox appears, the more likely you are to beat out the opponent's move. The last frame of the move should be as low as possible, because the quicker the move ends, the quicker you can perform another move. Hitboxes should be as big as possible, and hurtboxes should be as small as possible. You want lots of disjoint. That is, you want the hitboxes to reach far beyond the hurtboxes. But those were just the geometric aspects of the game. Each colored hitbox has its own collection of numeric data, such as damage and knockback. I was unsatisfied with the existing tools for looking at frame data for the Smash game I played, Project Plus, a mod of Brawl. There was a Discord bot that would spit out frame data on request and hand-curated forum posts, but the data was mostly manually compiled. A lot of data was missing, and when the game was updated, the bot and threads needed a lot of manual changes. The UX of both of these were lacking. The Discord bot requires knowing the exact name it uses internally for each character and move, and the forum threads are scattered around and hard to find. The graphics used in both of these were misleading due to using a perspective projection while not allowing inspection of the true 3D nature of hitboxes and hurtboxes. I do want to note that my final solution does have some downsides compared to these, but going into that right now would ruin my narrative. Now here I was with my cool new library for reading Brawl data and a problem that needed solving. So I set out to make a website that includes an interactable 3D render instead of just GIF recordings, allows users to step through the animation frame by frame. Every detail of every character should be automatically extracted from the game while making the most important data prominent and easily accessible. The whole process should be end-to-end automated, so I can update the website within a day of new updates coming out, and it should be optionally accessible via a Discord bot that links to the website. This will encourage people to use the website when possible, but also allows the Discord bot to smoothly integrate frame data with relevant community discussion. The first step was choosing a graphics library. A tricky problem to solve here was how do I provide graphics for both a website bot and a website, Discord bot and a website. A Discord bot can only display GIFs, while I want my website to have an interactive 3D renderer. The solution was WGPU. WGPU is a Rust graphics library that abstracts over the major desktop, mobile, web graphics APIs. WGPU is also the implementation of WebGPU used by Firefox. But wait, if WGPU is a WebGPU implementation and can use WebGPU as a backend, isn't that a recursive dependency? Well, it turns out that's fine because only the backends available for the compiled platform are included. On Linux desktop, the stack looks like this. The app is compiled natively, statically linking WGPU in the binary, which will dynamically link to Vulkan to make the needed API calls. In the Firefox web browser, running on a Linux desktop, the stack would look like this. Notice how WGPU is included in the stack twice, once in the app and once in Firefox. First, we have our app compiled to WASM statically linked to WGPU. The version of WGPU in our app ends up being a very thin layer over the JS WebGPU API. Since WGPU is a WebGPU implementation, there is very little translation to perform. Firefox then routes accesses to its WebGPU API to its statically linked copy of WGPU. Being able to run the same graphics API natively on both web and desktop is perfect for my needs. The renderer built on top of WGPU will live in brawllib, and then two different crates will make use of it. In the first case, the website will have a crate compiled to WASM, which will form the app, and that runs on the web page. WGPU and Winit just handle this for me, and I can run the same app both natively and embedded in a web page. Running natively is useful here for testing purposes, while in production it will only ever run in a web page. And in the second case, the same renderer will be compiled natively with some extra glue to output GIFs. The website generator crate will be compiled natively. As part of generating the website, it will manually step through each frame of the animation, extract the frame buffer for each frame, and export it to a GIF. These GIFs get embedded in chat services like Discord anytime the page is linked, which is particularly useful when the Discord bot posts the link. But the GIFs are unused when actually visiting the site. It's honestly so cool that Rust and WGPU let me share my renderer like this. I don't know of any of a stack where I can do that, although I haven't really looked. Naturally, to host a website, I need a web server. When I started the project, Rocket was very popular, so I chose that and got to work. I was loading in the Brawl data on startup, processing it to high-level structure, and then generating the page containing frame data on each page request. This worked, but I was worried about how well it would scale. My site won't be known outside the competitive community, but it could still be hit pretty hard from that alone. Thinking about this problem more, I realized, oh, my site is completely static. Why don't I just generate every possible page, store them to disk, and serve them the old school way? So I ended up rewriting my website to generate a static site instead of being served through Rocket. The whole site is stored in an Oz S3 bucket with Oz CloudFront in front to deliver content from a server closer to the user when possible. An unintended bonus is that I never have to worry about the server going down because it's completely serverless, perfect for my little hobby project. I have a web page per character action, and the total storage for each is on average 400 kilobytes. Each character has about 500 in-game actions, and there are about 40 characters in each game and multiple games. This results in a total of somewhere around 30 gigabytes to store the entire generated website. My upload speeds are terrible, so uploading 30 gigabytes wasn't really an option. So my solution here was to spin up an expensive EC2 instance for half an hour, upload the site generator, run the generator, and then push the results into my S3 bucket. I'm not a web dev by trade, but serving the page, including an entire Rust renderer within 400 milliseconds with cache disabled, seemed pretty good to me. And then I needed a UI. HTML is pretty handy. I can just make a bunch of pages and link between them for navigation. Pretty standard stuff. But if I want to have an interactive renderer, then I'm going to need some fancy UI to control it. That leaves me two options. Embed some UI within the WASM app. I could use one of the embeddable Rust UI crates like eGUI or Iced. Use native HTML UI, and hook it up to my app with WASM bind gen. I opted for native HTML UI because it would more naturally integrate with the web page. But if I had a reason to run my app outside of the browser, It would have made a lot more sense to integrate the UI within the app, and I probably would have used eGUI to do that. I've played around with eGUI for another project, and it's really nice. So my final UI looked like this, and I'm pretty happy with it. The numbers are clickable and set the renderer to render that numbered frame. The rest are various toggles and state you can set. WASM bindgen is pretty clunky to use directly. A lot of casting to different types, and you have to mem-forget, aka leak closures, to avoid runtime errors due to the closure being destroyed on drop, despite sending a reference off to the on-click. I'm sure you're thinking, surely not. But at least at the time I wrote the code, it was the intended design. But it gets the job done, and I didn't have to write too much of it. It also handles window resizing and mobile screens pretty well. The screenshotted code is the code that processes input to the perspective checkbox. It finds an element in the DOM with a specific ID and sets its on-click property send an event to the app. In this case, that event will set whether the renderer should use or not use perspective projection while rendering. Some user input, such as controlling the camera, will be responding to mouse clicks on the actual canvas. Winit can handle this directly, and I don't need to touch WASM bindgen at all for that. Normally you could use something higher level like U instead of directly using WASM bindgen, but I think I wanted more control to better integrate with my WinitW GPU app. And now I'm going to give a quick demo. No, I can't. I don't seem to be able to follow the link. Does that? Thanks. So this is the project. We have the frame data for march forward air or attack air forward. And we've got our 3D renderer here. And so we can interact with this and zoom in, zoom out. And we can run the animation like this and jump to different frames. And then we've got all sorts of information extracted from the hitboxes. So things like damage and knockback. And then we've got the scripts from the actual game. So these scripts are what actually defines this data. And then the rest of it is like processed from the scripts to drive all of this stuff. I think it's worth mentioning where I had to cut corners to make this work. Currently, WebGPU is still unstable, so WGPU is running over WebGL instead. This has caused me problems such as no support for anti-aliasing or wireframe rendering. I also need to use a fork of Winit that makes use of the unstable Web API resize observer. Without this fork, Winit cannot properly handle flowing the canvas within the web page. That's it. Thank you for listening. Oh, yes. Any questions?
That was really cool. How expensive was it to generate all of the game?
It normally costs like $1 to run. Oh, how expensive was it to run the EC2 instance that generates the website? It completes in about like half an hour to an hour, and it costs like $1. So it works.